Welcome to another deep dive. I've always found the idea of order emerging from disorder just utterly fascinating.
Yeah, me too. Like, how can something so unpredictable ultimately lead to something so structured? It's really remarkable when you think about it.
And that's exactly where chaos and complexity theory come in. These theories explore just the dance between randomness and order, simplicity and complexity.
Right. And the really amazing thing is how these theories apply to so many different fields. Like, we're talking everything from physics and biology to economics and even social sciences.
So today on our deep dive, we are going to unravel these two captivating theories, understand their key characteristics, and explore some real-world examples that'll hopefully make your jaw drop. Ready to dive in?
Absolutely. Let's do it.
Okay, so first up is chaos theory. Now, this theory centers around this idea of, well, deterministic unpredictability, meaning that things follow rules. But even the tiniest differences in the beginning can lead to dramatically different outcomes down the line.
Yeah, exactly. It's like that classic example, the butterfly effect.
Right, the butterfly effect. So, the idea that a butterfly flapping its wings in, say, Brazil, could, in theory, set off a chain of events leading to a tornado in, I don't know, Texas.
And it sounds crazy, right? But it highlights this crucial point about chaotic systems. They're incredibly sensitive to these initial conditions. So even if we know all the rules, even if we have all the data, those tiny, almost imperceptible differences at the start, they can completely throw off our long-term predictions.
So we're saying that even with perfect knowledge, predicting the future in these systems is basically impossible.
In a way, yes. Like, think about it on a larger scale, the formation of the universe. Tiny quantum fluctuations, like way back at the very beginning, may have actually determined the large-scale structure of galaxies billions of years later.
Oh, wow. Okay. That is mind-blowing.
Right. It really is. And that's the power of this butterfly effect, like on a cosmic scale. But here's the thing. It's not all just random chaos. Within this apparent randomness, there's often a hidden order. And this is where we get into strange attractors.
Your strange attractors. Okay. And these are...
Think of it like this. Imagine a pendulum swinging erratically, right? In a really turbulent flow. Now, it never settles into a predictable path. Instead, it kind of traces out this complex, non-repeating pattern. That's a strange attractor at work. It's like a hidden signature within the chaos.
Interesting. So these strange attractors are like the system's fingerprint, and they suggest that there's actually an underlying structure within all the chaos, even if it doesn't seem like it at first glance.
Exactly. And what's really fascinating is that these patterns, these strange attractors, we can actually represent them mathematically using equations.
Oh, interesting.
And unlike traditional equations that kind of deal with stable points, these equations for strange attractors, they capture that dynamic, that ever-evolving nature of these chaotic systems.
Okay, got it. So we've covered chaos theory, unpredictable outcomes, butterfly effect, strange attractors. Now let's shift gears and dive into complexity theory.
All right, so with complexity theory, we're moving away from just the idea of things being chaotic, and we're focusing more on how interconnected systems, well, how they become complex, how they evolve.
Okay.
And a key concept here is something called emergent properties. This is the idea that the whole is actually greater than the sum of its parts.
So give me an example of what that looks like in real life.
Sure, so imagine an ant colony, right? Now, each individual ant, they follow pretty simple rules. Yet, collectively, they create this complex superorganism, one that's capable of building like these intricate nests, foraging for food and defending their colony. That collective intelligence, that's an example of an emergent property.
So the colony's intelligence, it's not found in any single ant. It's found in how they all interact.
Precisely. And it's not just ant colonies. Think about the human brain. We have billions of neurons firing, all interconnected, and from those interactions, our thoughts, our emotions, our consciousness, they emerge.
Wow, it's remarkable. But, this all sounds like a recipe for chaos.
Yeah.
How does order emerge from all this complexity?
Well, that's where self-organization comes in. So think about like a flock of birds, right? Each individual bird responds just to its immediate neighbors. And yet from these simple local interactions, this beautifully coordinated flock, it just emerges.
So no grand plan, no single bird leading the way, just simple rules and interactions leading to this complex, beautiful behavior.
Exactly. And this same principle of self-organization, it's at play in so many complex systems, whether it's, the formation of galaxies, the patterns in weather systems, or even the way our cells organize into tissues and organs.
Amazing. And, earlier we talked about this idea of self-similarity in chaos theory, like with fractals and things.
Hmm.
Does that concept apply to complexity theory as well?
Absolutely. Self-similarity is actually a key concept in both of these theories. It emphasizes how simple rules repeated at different scales can generate these incredibly complex structures.
Okay, so no grand plan, just simple rules and interactions creating complexity. Amazing. Now, what role do feedback loops play in all of this?
Feedback loops. They are absolutely essential for how these complex systems, how they adapt, how they stabilize. They basically govern the system's behavior over time.
Okay, and just remind me, there are different types of feedback loops, right?
Yeah, so you have negative feedback loops, which essentially help to maintain balance, to keep things stable. Think of like a thermostat. Uses negative feedback to keep the room temperature steady. And then you have positive feedback loops, and those amplify change.
Right, right. Okay, so negative feedback keeps things in check, while positive feedback can either lead to, like, growth or instability, right?
Precisely. And this interplay between positive and negative feedback is constantly happening in complex systems. It's what drives their dynamics, whether we're talking about, ecosystems, economies, even social systems.
Okay, so we've covered a lot of ground here, but let's get to this so what. Why should we care about these theories? How do they apply to our lives?
Well, understanding chaos and complexity theory, it can really change the way we see the world, the way we approach problems.
Okay, give me some specific examples.
For instance, think about weather forecasting. We all know how difficult long-term weather predictions can be, right?
Yeah.
Chaos theory helps us understand why that is. It shows us how those small initial atmospheric variations can cascade into these huge differences in weather patterns over time.
Well, that makes sense. So chaos theory is basically saying don't trust the 10-day forecast.
Well, maybe not entirely, but, it emphasizes the limits of our predictive power.
Okay, what about other fields?
Let's take finance. Complexity theory sheds light on how interconnected markets are and how this interconnectedness can lead to these sudden, unpredictable events like bubbles and crashes.
Okay, yeah, the economy. Never predictable.
Exactly. And it goes beyond these specific examples. Even in managing organizations, understanding these theories can help us to design structures that are more resilient, more adaptive to change.
So you're saying that by understanding chaos and complexity, we can better navigate the uncertainties of our world.
Absolutely. And it really leads us to think differently about problem solving, about decision making. If seemingly small actions can have these massive unforeseen consequences and complex systems are constantly evolving, well, how should we approach challenges? How should we plan for the future?
Hmm. It's a lot to ponder, that's for sure. I mean, it really underscores how much we don't know, how much is outside of our control.
Yes, but it also highlights the beauty of these systems, the interconnectedness, the constant evolution. There's a certain wonder in that, don't you think?
Yeah, there is. All right, well, this has been a fascinating deep dive. It's given us all a lot to think about.
Absolutely. Glad we could explore this together.
Thanks